Namaste, my dear teacher and my friends. Today I'm going to present my work on the topics tangent plane and normal line to the surface. Tangent plane, let S is to R equals to RUV be the surface and P be the point on it. Then there are infinitely many tangent at P. Among them, R1 and vector R1 and vector R2 are tangent to U corp and B corp respectively. From this we can say that a plane spanned by R1 R2 is called the tangent plane at P. These are the example of tangent plane. Similarly, normal line, let S is to R equals to RUV the surface and P be the point on it. Then vector R1 and R2 are the tangent at P. Now a line product of R vector R1 and R2 which is perpendicular to the tangent plane at P, it's called the normal line at P, and we can take out the unit vector denoted by n vector equals the product of vector R1 and R2 and divided by the modulus of the product of vector R1 and R2. Tangent plane to the surface R equals to RUV. Let S is to R equals to RUV be the surface and P be the point on S, with vector OP equals to vector R, then R1 vector and the vector R2 are tangent at P. Let us suppose omega be the tangent plane at P, then vector R1 and vector R2 lies in omega. Now if R be the position vector arbitrary point T on omega, then R minus vector R comma R1 vector comma R2 vector lies in omega. Hence R minus R vector comma vector R1 comma vector R2 equals to 0, and from there we can write that R minus R vector into R product of R1 vector and R2 vector equals to 0, which is the equation of tangent plane. Tangent plane to the surface fxyz equals to 0. Let fxyz equals to 0 be the surface and pxy be the point on it. We suppose that omega be the tangent plane at P. Hence gradient f equals to df by dx, df by dy, df by dz is a gradient at P. Then gradient of f equals to df by dx, df by dy, df by dz is normal to the tangent plane omega. Now if rxy arbitrary point on the tangent plane omega, then x minus x, y minus y, z minus z lies in omega. Hence product of x minus x, y minus y, z minus z and df by dx, df by dy, df by dz equals to 0. And similarly from here we can write that product of x minus x df by dx plus product of y minus y df by dy plus product of z minus z into df by df equals to 0, which is the required equation of tangent plane. And normal line to the surface R equals to RUV. Let S is to R equals to RUV be the surface and P be the point on P with OP equals to R. Then product of vector R1 and R2 is normal at P. We suppose this line is L. Let R be the position vector of arbitrary point T on L. Then R minus vector R is parallel to L, or R minus vector R parallel to the product of vector R1 and R2, or R minus vector R equals to lambda product of R1 into vector R2, which is the required equation of normal line. Normal line to the surface fxyz equals to 0. Let fxyz equals to 0 with the surface and pxy be the point on it. We suppose that L be the normal line at P. Hence gradient of f equals to df by dx, df by dy, df by dz is gradient at P. Then gradient f equals to df by dx, df by dy, df by dz is parallel to the normal line L. Now if rxyz be the arbitrary point on L, then x minus x, y minus y, z minus z equals to lambda df by dx, df by dy, df by dz. And from this one we can write that x minus x divided by df by dx equals to y minus y divided by df by dy equals to z minus z divided by df by dz, which is the required equation of normal line. Okay, thank you all my friends. I have finished my presentations.